So solid mechanics is kind of like an extension of statics in that a lot of the ideas of statics are going to be really helpful to know for solid mechanics. So in statics, the idea is that you're talking about things called rigid bodies. So for rigid bodies, basically the assumption is that it's not going to change like shape or size or anything. Ooh, that's really thick. Okay. So like if I have some object here, like this beam, right? I put some forces on it. Let's say I put like a force like this in the middle and here, right? So in the statics case, we have rigid bodies, which basically means that we would assume that this thing is going to hold perfectly as the shape of like a rectangle. And if the force is balanced and it's not moving, and both of these we're going to assume that things aren't moving, so like no velocity, no acceleration, no angular acceleration. But the difference with solid mechanics, it's also called mechanics of materials, so I'll just try like is that we assume that they can deform. So if the stress inside this beam gets strong enough, well, kind of intuitively what we would know would happen is it would kind of bend down like this, right? And so in solid mechanics, we're going to see what happens if we actually allow it to deform and fail. And we're going to see in what ways it fails, like maybe it can fracture or it can bend. Yeah, but there's still some statics you got to know. And obviously, it's not like the entire semester worth of statics. Like statics is a whole class, but you need to know all of it. So this is kind of like the 20% of statics. It'll get you like 80% of the way there. So like I said earlier, the basic idea is equilibrium. So if you add up all the forces on a system, they have to equal 0, which means that my fx has to equal 0, right? All the forces in the x have to equal 0. So if I add up all the forces in the x direction, that's 0. And then also same thing for the y direction. And then Newton's second law for rotation says that if I sum up all of the moments or torques, that has to also equal, I believe it's like the moment of inertia times the angular acceleration. But in this case, again, that just equals 0. So this just becomes 0. In the case of 2 dimensions here, we only have one rotation to worry about, and that's around this out of the page axis like this. So we can go ahead and say that the sum of, I think we usually use m for moments, has to equal 0. And so this right here gives us 1, 2, 3 equations that we can use in 2 dimensions at least. And then for 3 dimensions, we're going to be able to add the forces in the z direction. So in the 2D plane right here, I'll just have forces in this direction, and I'll have rotation around this z-axis. But in 3 dimensions, I can have rotation around all of these axes, and I can also have forces in all those directions, which means that I have 6 total equations that I can use. So if I have 6 unknown forces, then you'll be able to solve for all of them. And so this is one of the most common things you're going to see in statics is we've basically got a beam right here, and then we're seeing that has this applied load. I think it's called a distributed load. So basically their idea here is that there's a weight distributed across this entire load right here, and we have W to describe it. So this will have units of force per unit length, so something like newtons per meter. And the idea is if I multiply by an amount of length, it'll tell me how much force is across that entire area. I have an applied load P here, that's just a force. And now if we do a free body diagram of this beam, free body diagrams are things that you would do a lot just to like see what forces there are. The way that they usually do these is you draw the object. So like in this case, we'd have the beam, and we'd think about what forces are applied. So obviously we'd have our P, and we'd have this distributed load, right? Comes all the way across here. It'll go down. This is a poor drawing, but you get the idea. We'd have our W right here. And then in order to balance these, we have 2 supports in this case. We have a roller right here. And if you think about a roller, it's not going to stop it from sliding side to side, but it will stop it from falling into the ground. So no matter how much I push down right here, the roller is going to be able to support it with a force that points up. So one of our reactions right here, we're going to call this BY because it's in the Y direction. And we also have a pin right here. So if you think about a pin, it's going to stop it from sliding past in any direction, but it won't stop it from rotating. And so what we say is that there's some force, but we don't know the direction, right? So basically we have 2 unknowns, like a force and an angle right here. So we don't know theta, and we also don't know the magnitude. Another way we can write this with 2 unknowns is we can usually say like the y component and the x component. And this is usually how you're going to see it written. So we'll have our y reaction at A, and we'll also have the x component of the reaction at A. And if you think about it right here, we have 3 unknowns, and assuming that we know W and P, we can go ahead and solve for this. But there's a problem in that I haven't really told you how you exactly figure out this distributed load thing, and that's because we haven't talked about the centroid. So basically the idea here is that the area of this entire load with the applied distributed load can be simplified to just a single force at the centroid. So the centroid is kind of like the center of mass if you assume that the density is evenly distributed. So if you imagine I just have like a simple square here. So the centroid is going to be right in the middle right here, right? And so what I can say is that if this is an entire like area of a load right here, I can replace it with one force right in the middle. But to be more precise, what we say is that the centroid is kind of like the weighted average of the heights multiplied by the area. Now that's a little bit abstract, so I'll try and kind of give you more of an idea of what I mean. So like let's say I have something that's comprised of like a square right here, and then let's say I've got like a hole, right? So basically this entire shaded region right here is the area of my thing. Well, what I can do is I can say, all right, let me break this up into its composite areas. So I know I'd have an area right here in the middle, right? And I'd also have a area right here. Technically this would be a gap, but you could replace that with a negative area and it's the same thing. So let's say like, I don't know, if you're trying to do something where you have like a semicircle and it's connected to like a square, right? And I want to get the centroid off like this baseline right here. I could get the centroid of the square and then the centroid of the semicircle. And then I could basically do a weighted average of these based on the area. So if we call this like our y bar 1, and then this right here, or I guess y tilde would be more correct, 2, and then this area of this semicircle right here is A2. The area of this right here is A1. Then what we would have is that the centroid, basically y, which would be probably somewhere around here, right? So this right here would be our y bar, has to equal our y tilde 1 A1 plus y tilde 2 A2, and then it's a weighted average, but we have to basically normalize for the area, so we just divide by the area. So for here, all we would do is we would subtract. So if we're doing, let's say, like the y bar off this right here, so we'd have a 1 right here, and we'd have a 2 going right here. So our total y bar for this one would be equal to, essentially, if you call this like y tilde 1, y tilde 2, this would be, right, y tilde 1, A1, but because we're subtracting this and we're removing it, it would actually be a negative. So basically we're just, it's like a negative area because we're taking it out of this rectangle right here. And then we'll have plus y tilde 2, A2 all over negative A1 plus A2. And then you can kind of extend this process with an integral, like the definition of your centroid is that y bar is equal to the sum of all of your y tildes at some location differential area over adding up your differential area. So anyway, this is a long-winded way of saying that we can replace this distributed load right here with an equivalent load that's just equal to the area of this rectangle right here. So the force per length times the entire length right in the center right here. And then what we would do is we would be able to use our three equations of equilibrium to solve for AX, AY, and BY. So for example, like let me just come over here for a second. I could do like a sum of the force or the sum of the moments about point A. That would get rid of these right here. I know this has to equal 0 because we're in equilibrium. So then I would know this has to equal the length of the beam, which I called L, times BY, if we're assuming that this counterclockwise direction is positive. And then we would have to subtract this force and this force P right here, right? So I'd have an L over 2 times my W times L, right? Because this is the area under this rectangle, which represents the entire load. And then I'd also have to subtract an A times L. Because each of these are the torques, because my force is always perpendicular to my length. Because remember, torque or moment, they're just two words for the same thing. Is equal to R cross F, where R is the vector from where we're measuring to the location. So since I said we're doing the moments about point A, we'd have point A right here, and our R vector would basically go from here to here. But since they're perpendicular, this just becomes magnitude of R F sine theta, and theta is 90 degrees, so this comes out of here, right? So this is the magnitude of the torque vector, or the moment, same thing. So I'd be able to solve for By right here, assuming I know all of this other stuff, right? I think you could divide through an L if you want to. And then what I would do is I'd be able to sum all the forces in the y direction, because I already know By. Ay could be what I would solve for, and then I'd also have a W and P to worry about. And then if I sum all the forces in the x direction, it would actually just give me Ax, which has to equal 0, and that's because basically the pin isn't supporting any kind of forces in the x direction. So now we can move on to supports, looking at them more generally. There's a lot of different kinds of supports. We've already seen some of them. So this right here is the pin support. We've already seen that's just going to give us a force, but we don't know its direction. We could also show this as two components of the force. Either way, it's two unknowns. So we'd have like our reaction in the y and a reaction in the x. This right here is a roller at a slant, and basically the idea is that it can't support any motion along, but it can restrict motion perpendicular, so we'd have a reactionary force right here. Same thing with this is called a rocker. Same idea. You can also have something called a collar, where basically we pin it to something that can only slide along here, which means that the force it can react with. Basically, if you imagine like if I tried to push this in against this bar, it would resist that, or if I tried to pull it away, or if I pushed it parallel, then it'd be able to slide. So this can have a reaction in this direction, or technically it could also have a reaction in this direction. And then the last kind of support is one with three unknowns, so this is called the fixed support. So this is going to stop rotation and translation. So there's going to be a reaction in the x and y to stop any kind of force, and also any kind of bending moment is going to come with a reactionary moment to stop it. So if I put some force here, it's going to get stopped by this. If I put some force here, it'll be stopped by this. And if I put some moment right here, it'll be stopped by this. So the fixed support keeps it all in static equilibrium. So now we're going to talk about another important concept, which is the two-force member. So if you imagine we've got like some complicated structure right here, and let's say I want to do a free body diagram of like this link right here. So we've got this thing right here. It's pinned right here, which is going to give me two forces, or two unknowns. Really, it's one force, or two components. You get what I mean. We're going to have one right here in this direction. We're also going to have one right here. We know its direction, but it's not its magnitude, which means you have 1, 2, 3, 4 unknowns, and we can't solve for it unless we use the idea of two force members. So the concept here is if I look at some object which I know is in equilibrium and it has two forces, one at each end, then I know that these forces have to be collinear, so along the same line, and equal in magnitude. Because think about it, if they weren't along the same line, like if I had something like this, where like one pointed this way and one pointed this way, then it would want to start rotating like this, right? So the only way you don't get that rotation is if they point along the same line, and then they also have to have the same magnitude because they have to cancel out. If one was like greater than the other, then it would want to start accelerating in that direction. So that means that if we go here, we know that the reaction in this pin, because this right here is actually a two-force member because it's pinned on one end and pinned on the other end, has to be along this line right here. So now that we know that we'll have a reactionary force right here, and one right here, and one right here, and we don't know any of their magnitudes, but we do know all of their directions, which means we have three unknowns, and we can solve for it using our three equations. I don't know if I mentioned this earlier, but summing the moments works around any point, so usually it's just best to pick the most convenient point, which is where all of the forces usually intersect. So like I see right here, RC goes through this, and also RB goes through here. So if I sum all the moments right here, then I know that there's going to be nothing from RC or RB, and I basically would just have an equation only in terms of RA that would be pretty simple to solve. Now, one thing I want to talk about that you might be a little bit confused by is this applied moment right here. Now, normally we think of moments as forces kind of acting along some distance, right? So it might be confusing, like we have a moment right here. Wouldn't there technically have to be some force associated? And then at that point, why wouldn't we just like write the force, right? Well, the idea is that there's something called a couple moment. So if you imagine, like let's say I have a force right here going up, and then I also have a force right here going down, right? So in between them, if I just have like some object here, right, where that's actually feeling these forces, if I pick some point right here, what I would do is I would add the moment basically going this way from this one, and also the moment going this way from this one. But if I were to take this point and I were to shift it to the left a little bit right here, what I would see is that this one would get a little bit longer, right, which would create a longer radius and thus more torque, but this one will get a little bit shorter. And if these forces are equal and opposite, which they would need to be for this whole thing to be in equilibrium right now, then the amount that this gets longer and the amount that this gets shorter would balance out in such a way that I would actually see the same torque here, here, or any point along this beam. Now the thing is, summing the moments isn't just along points on the beam. I could also pick some point out here. But again, you could prove to yourself that basically the lengths that these each lengthen are going to be equal in such a way that the torque at this point is the same as the torque at this point or any of the other points. Another way you can think about this is, since we're multiplying by the sine, the effective length that we get is the perpendicular length, which means that we basically have the same length right here that's perpendicular to that force, and then same thing on this side. So if we come down here, basically what we're saying is that on this member, there's an applied couple moment of 4 kilonewton meters on this member right here. And now the last thing we have to talk about is the idea of internal forces. So I said earlier that everything is in equilibrium, right? We're assuming that it's not moving. But that means I can pick any component of this thing and it shouldn't be moving. So like earlier we saw I picked this L. I could have also picked this little rectangle right here that's pinned. So if I did that, I would have my pin joint right here. So I'd have a force in this direction and a force in this direction, right? Reaction Y. Other way, this would be the X, right? X, and this would be the reaction in the Y direction. And then I'd also have my reaction from this pin. I would have to write it like this. Because I assumed that the force is going this way, if you kind of think about it, basically the pin is pushing this guy to the right. So if I think about it from the perspective of the pin, it's getting pulled to the left from this. Or you could just think about it in terms of Newton's third law. Basically, when you look at the same force from two different objects that are pinned together, you have to switch which direction the force is being looked at. But this also means that I could just cut through a section of one of these things. So you can see right here, I've got a beam. If you want to make sure you have the ideas of like static equilibrium down, then it might be a good idea to try and solve for the reaction forces. So go ahead and get set up with a free body diagram right here. I would have my beam, and I'm going to look at all the forces on my beam. I'd have reaction in the X, so we'll call this like AX, AY. I would have tension from this rope right here. It would only pull in one direction, and the direction is given by this 3, 4, 5 triangle. So from there, you'd be able to figure out the angle, right? I'll just call this like, I don't know, F from rope. And then lastly, I would have this 500 kilogram weight that's going to create a 500 kilogram times gravity, 9.81 meters per second squared force, right? And now we have 3 equations, 3 unknowns. You'd be able to go ahead and solve for all the reactions right here. What we could also do is we could just look at a section of this beam. So for example, let's say I just like cut through it here, right? So I have my beam right here. And then let's just say like I pick right in like the middle, right? So like right here, I want to cut it. Okay. Now I know that this section of the beam has to be in equilibrium, which means that this force AY and this force AX has to balance with some force being carried inside the other side of this beam right here onto this one. So I know that there has to be some force basically that would push back like this. And then there could also be some force pushing back here, and there could even be a moment because this side right here essentially has to be fixed if the whole thing's in equilibrium. And our convention for this is to break it into the components. So we say that basically perpendicular or normal to this cut, we have the normal component of the force, and the shear force is always clockwise. So in this case, it would be down on the right side or up on the left side. So we'd have our shear right here, and then the moment causes it to bend up. That's our positive convention. So the moment would be here in this case. And then if you had a beam on the other side, it would all have to balance out with Newton's third law, which means that, so in this case, we'd have our FR, right? And then we'd also have our downward weight force. So we'll just call this W. So it'd have to balance out. So we'd have an N in tension the other direction. We'd have a shear pointing up because it's clockwise. And then we also have a moment like this. You can see that all of them point in the opposite direction, so they would cancel out when we put them back together. And if we could basically combine these free body diagrams, then we would get this one right here. So now if I use this big free body diagram to solve for my reactions AX and AY, and then I use this cut, I would be able to solve for M, N, and my shear, because I would be able to use my 3 equations of equilibrium to this cut. And so that's the basics of statics, at least what you're going to need to know to get started with mechanics of materials. Next time we're going to talk about stress. Yeah, I'll see you there.